Hello, everyone, and welcome to what is sure to be a lengthy discussion of potential energy and equilibrium. So, first off, let's review what we know about potential energy, right? The ability to produce change. So, we've looked at a couple of different potential energy storage mechanisms. First off, consider the ideal spring. Right? We know that the ideal spring, or Hookean spring, if you will, follows Hooke's law, which says that the force exerted by that spring is equal to negative kx, where k is the spring constant, or strength of the spring, and x is the amount of elongation, or compression. Right? This is a special kind of usually cylindrical spring, follows this nice linear pattern. So when we graph that force as a function of elongation or compression, right, we get a graph down in either the second or fourth quadrants, as the force and the elongation or compression are always in opposite directions. And we then defined the elastic potential energy to be the negative of the area under the curve of that graph. If we allow it to stretch, or if we stretch the spring an amount x, it is exerting a force we can call F sub s, and this area, right, the negative of that area, is the amount of elastic potential energy that is stored in that stretched or compressed spring. Doing a little algebra on that and employing Hooke's law, we came up with a math model that we've been using for elastic potential energy is 1/2 kx squared. And don't forget the little squared here, which gives us an amount of stored elastic potential energy in joules. We also looked at gravitational potential energy. In this case, we have a box of mass m, which is being lifted from the ground to some height we can call yf, or y, right, at a constant velocity, just to keep kinetic energy out of the picture here, by some constant applied force f of a. So as we did in class, we can create a little force diagram here where the applied force is balanced by the force of gravity because it's not accelerating. And that force of gravity, as long as we stay near enough to the surface of the Earth, and eventually we'll look at what happens if we don't, but that's in a different unit, right? We can see that this force of gravity, or the weight of this object, is going to stay constant and negative as it's being lifted, right? Directed negative because the force of gravity is down. So if we create a graph of the force of gravity versus height, we get a graph in the fourth quadrant. And like we did for a spring, we then, if we lift to a height y, we then defined the gravitational potential energy to be the negative of the area under this curve, right, of the force of gravity versus height graph. So once again, notice it's the negative of the area under the curve of force versus height. And this one's a little easier to do, without going through the algebra. It's just f of g times y, and f of g is mg, so it is, of course, mgy. Again, that's near enough to the surface of the Earth where we can consider the gravitational force to be constant. So let's generalize then, because this isn't just true for forces of gravity and forces exerted by springs. This is really true for any conservative force. Right, that we can define the potential energy, the stored amount of ability to produce change, right, to be the negative of the area under the curve of a graph of that force as a function of position. Now notice the use of the symbol capital U here. This is a traditional thing to do. In fact, you might see that on an AP test where they even write the ones that we've already written using a capital U. So like, for example, they may call it U sub S for elastic potential energy, right? Spring for S, and U sub G for gravitational potential energy. Okay, you can certainly use our symbols, they will understand them, all right? But generically, it's traditional to use a capital U for potential energy. I don't really know why that is, but that's what's used. Now, we were able to find potential energy functions for springs, Hookean springs, and for gravity near the surface of the Earth, because those functions were simple enough that we could find the areas under the curve just using geometry. But what if the function is more complex? Well, we now have a mathematical technique to find the area under the curve of a particular function. We can use integral calculus. So we can take this definition, the negative of the area under the curve of a graph of f with respect to x, and turn it into calculus. There we go. This is the same as this sentence. The potential energy is equal to the negative integral of the force with respect to position. Negative integral means the negative of the area under the curve of the force as a function of position. So we can do this. And just to show you that this actually works, let me show you how the calculus applies to the two situations for which we didn't need it, because we could do it geometrically. By the way, this is for one-dimensional conservative forces. Technically, we could take this into 3 dimensions and use a dot product, but they don't really. I've never seen them do that, so I'm going to stick with one-dimensional cases here. So consider the force of gravity. The force of gravity is, of course, near the surface of the Earth, just negative mg, right? If we get rid of the vector nature by putting in the direction. So if we plug that in for F, we get that the gravitational potential energy, and note here I am using AP-ish symbols, U sub g, right, is the negative of the integral of negative mg with respect to y, where y is the height. Well, the negatives cancel. That's why we chose to make it the negative of the area, so that we'd get a positive amount of energy stored. M and g, the mass and the gravitational field strength, so long as we are near the surface of the Earth, are just constants. So this is just the integral of a constant with respect to y, which is just mgy. So here's the calculus derivation of the gravitational potential energy equation. Okay, based on the force of gravity as a function of height. Likewise, if we look at a spring, a Hookean spring, right, where the force exerted by the spring is equal to negative kx, then we can plug in that force as negative kx, right, in here. The negatives cancel, so we get a positive amount of energy. K is a constant, so we really have the integral of k times a constant dx with respect to x. So if we add 1 to the exponent, 1 plus 1 is 2, divide by the exponent, we get 1/2 kx squared. This is the calculus derivation of the elastic potential energy. And note me using again here both symbols R's, which I like, and the older-fashioned AP-ish way, U sub S, right, for elastic potential energy. So if you take this in college, your introductory level calculus-based course, you might end up getting it derived this way rather than the graphical way that we did it in honors and so far in here. But we didn't really need the calculus, right? Just wanted to show you that the calculus definition of potential energy, it does work for the things that we've already looked at, but we didn't need the calc because the functions were simple enough that we could do this geometrically. But one other thing that they want you to do here is they want you to be able to look at some graphs and define some things on graphs. And these are graphs that we never really dealt with last year. So these are more complex and more specific to APC, which is graphs of potential energy as a function of position. Notice potential energy in joules and position in meters. So let's start out by graphing this function. Why not? It's a good function to look at. 1/2 kx squared. Obviously, the 1/2 and the k are constants. So what would a graph of potential energy as a function of x squared look like? Hopefully you realize it would be a parabola with its center at 0, 0. Certainly makes sense. When the spring is not compressed or elongated, there is no energy stored, right? So 0, 0 is a point on here. So this would be a graph of the potential energy as a function of position. Well, as we've usually done, when we have a graph, we tend to look at properties of the graph to give us meaning. And one of the first properties we always look at is slope. So what does the slope of a potential energy versus position graph represent? Well, from a calculus standpoint, every slope is a derivative. So asking what the slope of this graph represents is really asking what is the derivative of the potential energy as a function of position. Using our example here of a stretched or compressed Hookean spring, we can plug in this function for EE and take a derivative. Multiply by the exponent, subtract 1 from the exponent, and we get back kx, the spring constant times the amount of elongation or compression. But you might be saying, wait, I've seen that before. Kind of, right? Because kx is really the scalar part of a force exerted by a spring, Hooke's law, right? It's really negative kx because the force and the elongation or compression always act in opposite directions. So really, this is the negative of the force. It's the opposite of the force. Right? If we want to put this in here, right? Or we can say then that the force is the negative derivative of the potential energy as a function of position, with respect to position, or the negative slope of the graph. And think about this compared to that. Aren't those inverse functions? The potential energy is the negative integral of the force with respect to position, and therefore the force is the negative derivative of the potential energy with respect to position. Right? Those are inverse things. This negative, though, is really key. It's key to understanding and interpreting. It's also key on AP tests. Can't tell you how many times I've seen people lose points because they forget they're negative, and so their force ends up being opposite. And believe me, they give that as a choice because they want to see if you've remembered that it's the negative slope, right? Just like it's the negative of the area under the curve, right? So don't lose the negative sign here. So let's take a look at this function, this graph of potential energy versus position. And let's analyze the slope, the negative of the force, if you will, in terms of something we will call equilibrium. Okay, equilibrium is a condition that comes up quite a bit in mechanics. You're going to see it here. You're going to see it again in rotation. You'll see it again in oscillations. Equilibrium is special because it occurs when the net force is zero. And if you think about it, we actually, in honors, we did an entire model on balanced forces, right, when the net force is zero. So it's an important case. It's a special case, but it's an important case, and it's called equilibrium, when the forces equal out, right, when they balance, if you will. Now, if we look at our graph, there is only one point of equilibrium here, and that is 0, 0. Right? If you take the slopes of the tangent lines, right, the tangent line at 0, 0 would be horizontal and therefore have no slope and therefore indicate no force, since the force is the negative slope. Okay? But there are actually 3 kinds of equilibrium that they want you to know about on an AP test. Which kind is this? Well, to figure out what kind it is, let's take a look at what happens if we move to a little bit to the right of equilibrium, or if we move a little to the left of equilibrium on the graph, which in this case corresponds to stretching the spring a little bit to the right or compressing it a little bit maybe to the left. Okay? So if we stretch the spring a little bit to the right, look at the slope of the graph. What kind of slope is that? Well, to the right of equilibrium, all of the slopes are positive. But remember, the force is the negative of the slope. So while the slope to the right is positive, the force is actually negative. Don't lose that negative sign, right? The force is negative. Which means when you stretch the spring to the right, The spring is pulling back to the equilibrium position. It's a restoring force. That's what we defined it as back when we first looked at it. In a similar way, if we go a little bit to the left of 0, what kind of slopes do we have? We have negative slopes, but the force is the negative slope. So this would result in positive forces. So we go a little bit to the left, and the force pushes back to the equilibrium position. Another way of idealizing this, other than a object on a spring, okay, would be like, say, maybe a marble in a bowl. When the marble goes up the right side of the bowl a little bit, there's a component of the force of gravity which pushes it back down the bowl towards the equilibrium position, which is at the bottom. When it goes up the left side, there's a force of gravity which pushes down towards the equilibrium position, right, and moves it back to there. So this would be another kind of similar kind of looking graph. This kind of equilibrium is known as stable equilibrium because the oscillation, the vibration, if you will, is stable, really. So here's the technical definition. This occurs when small displacements result in a restoring force which pushes the object back to the equilibrium position. A mass on the end of a spring, bouncing right and left or up and down. A marble in a bowl has this kind of equilibrium. Okay? It tends to go back towards the equilibrium position. Note that this tends to be important when we do a unit on oscillations later in the year. This is the kind of equilibrium that we're going to want, because otherwise, we're breaking stuff and it's flying away. We're going to want to look at cases of stable equilibrium, which is what happens when things oscillate. Okay? Pendula, masses on the end of springs, vibrating guitar strings, vibrating columns of air, all these things, right, we can look at in terms of their oscillations and look at them in cases of stable equilibrium. Well, that's one of 3 kinds of equilibrium. What if we had a case where, let's say, a skier at the top of a hill between 2 valleys? Right, so we're looking at the gravitational potential energy here to be technical. Wouldn't that look more like this kind of graph? Right? Where at the top of, by the way, we're calling the top of the hill 0 position. Top of the hill is 0 position. Okay? 0 height, if you will. So if the top of the hill is here, right, that's where the equilibrium position is. And then as they go down the hill, of course, they have less potential energy as they get closer to the ground. Right? The ground being 0, potential energy, right? The top of the hill being 0 position, right? But a maximum of potential energy. This could also be, an alternate example would be balancing a pencil on its tip. Very hard to do. Okay? But if you could get it perfectly balanced, right, it would have a point of equilibrium at this point. But this is going to work differently than our stable equilibrium. Let's look at what happens when the skier moves a little bit to the right off the hill. Now, according to the function, the slopes to the right of equilibrium have what kind of slopes? Negative slopes. So they have what direction forces? Positive forces, because it's the opposite of the slope. So you move a little bit in the positive direction, and now you have a positive force acting on you. Well, what's going to happen to you? Well, that positive force is going to push you even more in the positive direction. So rather than pushing back towards the equilibrium position in the opposite direction, it's now pushing away from the equilibrium position in the same direction. This happens likewise if you move a little bit to the left of our equilibrium position. Now our slopes are positive, so our forces are negative. So if we move a little bit in the negative direction, we get a negative force, which would result in us accelerating in the negative direction away from the equilibrium position. Right? Once the skier goes off the top of the hill, the force of gravity would get him to accelerate down the hill away from equilibrium. Once that pencil is not perfectly balanced, right, you move it a little bit to the right, force of gravity is going to make it keep tumbling to the right. You move it a little bit to the left, force of gravity is going to make it tumble to the left. This is called unstable equilibrium. Not very original, but descriptive. When a small displacement results in a force that accelerates it away from the equilibrium position. And notice the shapes of the graph here, right? It'll be easier if you kind of think of these in terms of shapes that you see on potential energy versus position graphs, right? So stable equilibrium was that U shape. Unstable equilibrium is kind of upside down. Okay? So there's two kinds of equilibrium. The third kind of equilibrium would be like, let's say, a water bottle on a table. Okay? Which might have a potential energy function that looks something like this. This is the table, which is off the ground, so the ground is 0 height. Right? Ground is 0 height. Up here, it's on the table. Right? If you move it too far to the right, it'll fall off the table and go to the ground. You move it too far to the left, it'll fall off the table. But I'm not really concerned with these parts. I'm more looking at this part right here. Notice that, yeah, we have a 0 of equilibrium again at 0 position. But if we move it a little to the right, right, so we take that water bottle and we slide it a little bit to the right, not off the table, it's still on the table. Well, what's the net force acting on it? Yeah, it's still 0, right? It's just going to sit there. And if we move it a little bit to the left of equilibrium, as long as we don't push it off the table, again, net force is still 0, so it's still in equilibrium. This is called neutral equilibrium. When a small displacement results in 0 force, so the particle remains in equilibrium. So we have stable, unstable, and neutral, right, equilibriums. They will expect you to be able to both decide or describe the three kinds of equilibrium and decide whether an object is in equilibrium and what kind of equilibrium it may be in, right, by using the idea of the shape of the graph or, right, by using the actual definition of what it means. Okay? Doesn't get used a ton in energy. It's the first time I'm going to introduce it, but it will pop back up again, especially when we do the unit later on in the year on oscillations on vibrating objects, although there we normally are dealing with stable equilibriums. Okay, we're going to do a little example here. Now, if you're taking notes, and hopefully you are, there is a sheet that you can have that you can take notes on. It is, right, it's on the schedule doc. And you can take notes right on it, right? It's got this graph and everything, and this graph right on it. So take notes there rather than drawing it all out. So here we have a potential energy as a function of position. Right? Now, and here's the function. And it's a, more complex function than the ones we were just looking at. You may notice one weird thing, which is the potential energy is negative all the time. I know this is weird. There's a reason they're doing it. It's got something to do with universal gravitation, which is the very last unit we do. Okay, but it's traditional to kind of look at this at this point. So if you want an example of this, consider a marble moving along a roller coaster track-ish kind of thing, but we're deciding that 0, rather than being the floor, is the ceiling. 0 is the ceiling. So if 0 is the ceiling, our whole roller coaster is below 0 and therefore would have negative gravitational potential energy, would have less than 0. I know that seems weird. Why would you do that? There is a reason for it. I just don't have the physics yet. We'll get to it. Okay? But suffice it to say that there are strange cases where we can have negative amounts of potential energy. So if you need a example of that, again, think of gravitational potential, but putting your 0 at the ceiling so that we live underneath it. Okay, so marble going up and down a roller coaster track here. So, first thing that the question asks us to do is, let's draw the corresponding force versus position graph. This is potential energy versus position. This is force versus position in newtons and meters. Well, we defined the force just a moment ago to be the negative derivative of the potential energy function with respect to position, which is otherwise known as the negative of the slope of the potential energy as a function of position graph. Be careful, it's the negative slope. Now, there's all sorts of parts to this, so we've done these kinds of graphs before. You might remember that I said that the easiest way to do these is to kind of break them into pieces. And the easiest pieces are the linear pieces, right, where you can find the slope geometrically on the graph, and then you kind of connect everything up, right? So I'm going to break these up into pieces. The first piece I'm going to use is the first 4 seconds. And note that this goes on a little bit more than 4. Okay, but I'm just going to use the 4 seconds because those are the parts that are easy to read. Slopes are rise over run. So what's the rise here? -8 joules. And the run is 4 meters. So the slope is -2 newtons. But that's the slope. The force is the opposite of that. Be careful. So for the first 4 meters that the object travels, the force acting on it is not -2, it's +2. And it goes a little past that, right? Maybe down to about 4.5-ish, give or take a little bit, right? And they won't care as long as you're kind of in the ballpark there. Okay? So this is what I mean by, like, sometimes people forget the negatives and then their graphs end up upside down. So you get a couple of the points, but not all of them. Now, let's go from about, let's see here. I went from about 7 meters to about 11 meters. That looks like a nice linear part. So here the slope is up 4. Be careful, it's not 1, 2, right? You got to look at the scaling. It's up 4 and over 1, 2, 3, 4. Up 4 and over 4, right? For a slope of 1 newton, but that's not the force. The force is the negative of the slope, right? So it's -1 newton. And note I started it over here, right? Kind of here-ish. Ended it about here. Now, question is, what's happening in between? Well, in between, the slope is changing from -2 and then eventually coming to +1, which means the force is moving from +2 to +1. So the AP would allow you to draw like a diagonal line through here, right? And they'd be okay with that. Technically, if you actually do the calculus, it would be a little bit more like an S curve. Right? See the little S right here? They would allow you to do either one. If you did a diagonal line, they'd be happy. Although, you should try to get your equilibrium point to basically match up. See where it goes through 0 here should be where this slope is basically 0 there. See how those basically match up, more or less? And they'd allow a little fudge room, right? But if you were like off, if you like took your diagonal line and went from here over to here, right? So that it went through like 6 plus, they'd be like, no, that doesn't really match the graph, right? It's not at equilibrium over here. So you want to make sure it matches. But a diagonal line would work, a little S-curve would work. The last part of the graph is pretty obvious. The slope here is 0, the negative of 0 is 0, so the force is 0. So it's right on the axis. Here, is this a sharp corner? If it's a sharp corner, technically there's a discontinuity here. So you could do a dotted line. They'd probably accept that. You could do a very shallow S-curve or diagonal line. They'd probably be okay with either of those, right? Yeah, they want the numbers to be right, but they want it, you know, the connections to be a little bit more ballpark. But be careful that you're actually picking up points of equilibrium here, right? When the force is, the net force is 0, the slope is 0, right? Slope up here is 0. The force here are zeros, which is when it's on the x-axis. Again, be careful that it's the negative of the slope. By the way, I think this might be on the equation sheet, but just be careful with it, right? The negative slope there. Because otherwise, you'll get the same graph. It'll just be upside down. You won't get full credit. Of course, If it's a dreaded multiple choice problem, you'll just get the problem wrong, and that would be really unfortunate because you actually know a lot about it. So remember those negatives. Now let's talk about equilibrium, because we were just dealing with that. Where are the points of equilibrium? Well, remember, equilibrium is defined as when the net force is zero. Well, on a graph of potential energy versus position, that's when the slope is zero. But more simply, on a graph of force and position, it's when the force is zero, which is here at about 5 and over here. But what kind of equilibrium is it? Well, it's hard to tell from looking at this graph, but look at this graph. Look at the shape of it. Which one of the three does that look like? Looked like the first one. It looks like stable equilibrium. Note from our force graph, if we move to a little bit to the right, so we're going in the positive direction, we get a negative force, pushes us back. We go to a little bit to the left, negative direction, we get a positive force, we're above the position axis, right? And that pushes us back to equilibrium. It's that U shape on the potential energy graph, right? We also have ones over here from about 11 to 14. And since there is no slope at all, that's, of course, neutral equilibrium. So on this graph, we don't actually have an unstable equilibrium, which looks the opposite of this, right? Upside down. But they might ask you to do this kind of thing, right? They especially identifying points of equilibrium, right? But the type might pop up, and that's an extra point, or if you can name them. Stable, unstable, neutral. Now, do something a little weird here. Let's say the object has a total mechanical energy of negative 5 joules. Let's just say that's how much it has. Okay? This is its total mechanical energy. And they show that on the graph with this double line. Okay? This is the total amount of mechanical energy. What they want to know is, how much kinetic energy does it have at 4 meters and at 9 meters, when the object is at position 4 and at position 9? Well, first off, we need to remember what total mechanical energy is. I personally don't like total mechanical energy, as I've told you before, but the AP people use it, so I'm using it. Total mechanical energy, if you remember, is the sum of the potential and the kinetic energies. You add them all up, that's your total mechanical energy. Total mechanical energy stays conserved, constant, if you will, right, if there is no work being done and there's no friction to dissipate any energy, mechanically speaking. Right? If there's friction, your total mechanical energy will decrease over time because there'll be energy dissipated. If there's work being done by an external force, you could either increase or decrease your total mechanical energy. You'll notice here, our total mechanical energy is constant. Well, we can use this equation to solve for an amount of kinetic energy. It's the total energy minus the potential energy at any position. Well, we were given the total energy. It happens to be negative 5 joules. Can we find the potential energy at 4 meters and 9 meters? Of course we can. We were given a graph. Could be given a function and we could calculate it, but we were given a graph. So, from the graph, the potential energy at 4 meters is negative 8 joules. The potential energy at 9 meters looks to be about negative 6 joules. Oh, sorry. So we plug that in. Negative 5 joules minus negative 8 joules. Be careful with all the negatives. Right? That's a positive 3 joules of kinetic energy. So if it has 3 joules of kinetic, negative 8 joules of potential, it'll have a total energy of negative 5 joules. In a similar way, we can say that the potential energy at 9 meters is negative 6 joules. Plug it in. Negative 5 joules minus a negative 6 joules gives us a kinetic energy of 1 joule. With me there? So this is finding the amount of kinetic energy. Now, by the way, I didn't ask it, but once you know the kinetic energy, couldn't you figure out how fast it was going? You need to know its mass, because the equation for kinetic energy is 1/2 mv squared. right? But given the mass, you could then figure out a speed. Look at all the things we can figure out. Given its mass, we could figure out how high it is or what its vertical position is. So things we could figure out along the way. Now here's the weirdest question of the day. Between what values of x can the object move? What? It can move the whole thing, right? Well, not necessarily. Just because the function exists doesn't mean an object can actually be at all points on the function. Take a marble in a bowl. If you give the marble a little push and get it going back and forth, does that mean that the marble automatically has to go all the way up the sides of the bowl? No. Depending on how much energy it has, it may only go partway up the bowl on each side. So there might exist a place where it could go, but it can't actually reach because it doesn't have enough energy. So that's really what they're asking here, right? We can determine the x's that the object can actually have by considering what points can it actually get to, at what points does it actually have enough energy to reach, okay? How high up the sides can the marble go? And that's got to do with the total amount of energy we have here. And something special about kinetic energy. Right, so first off, remember the kinetic energy is total minus potential, right? Using the idea of total mechanical energy. But remember the kinetic energy is 1/2 m of v squared. Well, m and v, which is speed, right, and it gets squared anyway, are scalars. So your kinetic energy has to be positive. It's a little weird. We talked here about how a potential energy, say, could be negative. Let's say we've got a marble on a track, right, and we're calling the ceiling 0. Then technically its height is below 0. So we could define a negative potential energy. But we can't do that with kinetic energy because it's just the energy it's stored because it's moving. It has nothing to do with direction or something, right? So kinetic energy has to be positive. We go back to these, notice that, right, as it got to 9 meters, it only had 1 joule of kinetic energy. Not a lot. So it could keep moving, but as the potential energy gets less negative, which is actually bigger, less negative is bigger in scalar world, right? It's going to have less and less kinetic energy. So between what values of x can this move? Do you see it? When will the kinetic energy have to flip from positive, which is doable, to negative, which isn't doable? Maybe we should ask, where's the kinetic energy 0? Well, the kinetic energy is 0, right? Total energy of -5. Right? Kinetic energy is 0 when the potential energy is -5. In this case, right? Because -5 minus a -5 is 0. Well, where's the potential energy -5? At about 2.5 and about 10 meters. So the object, since the kinetic energy is always positive, it can't reach positions where the potential energy is greater than -5, which is actually a smaller negative number, right? These are scalars, not vectors. A smaller negative is greater. I know, for 1.5 years we've been talking about bigger negatives being bigger in vector world, right? But this is scalars now, so smaller negatives are bigger. Therefore, the object can move between 2.5 meters and 10 meters. This part of the track may exist. It just doesn't have enough total energy to get there. If it wanted to do the whole thing, right, it would have to be at least 0. If it had a bigger total energy than that, it could even fly off the end or something like that, right? So once you lock everything down and say there's this much total energy. There's little things we can do here with potential energy versus position graphs to relate to motion and kinetic energies and total mechanical energies that they will sometimes ask about. I've seen every 3 or 4 or 5 years maybe a free response-ish problem pop up on this kind of thing, and I've seen a few multiple choice questions here and there about it. The negatives are really important here, and scalar versus vectors, right? And total mechanical energy sometimes comes into play. Yes, you're welcome. This one was very long and very complex. Hope you enjoyed it.